You have the network stream up here, and you have packet after packet, and you have the network card down here that reads the packets from the network, okay, from the wire or wireless or whatever. And whenever a packet arrives that is destined to the host, then this packet gets copied to the operating system into some buffer in the kernel, in the operating system, okay? So there's one copy operation taking place, and if you want to access this data with your user-led application, which is usually the case, then this data has to be copied again into another buffer in user space. So if you want to sniff a packet, then it's copied once, so this is not avoidable. The copy operation from the network interface card to the operating system, it's just necessary. You need to have the packet data in memory at some point. And then the second copy operation takes place because you want to, well, print it to the screen or something, the data. And if you want to write it to a dump file, like the situation down here, there is a third copy operation where you actually write the data to disk. Okay, and you might already know that these copy operations are usually very expensive. Okay, they take some time. You need to allocate memory, you need to write memory data into that memory, you need to free that memory, and all of this usually happens on a heap or something like that, and you have to organize this memory structure, so it takes some time. And also, of course, writing to a hard drive is, well, like the worst thing you can do because the hard drive is slow and also takes a lot of time. So if you want to design a high-performance packet sniffer, you have to reduce these as much as possible. But I'm going to talk a little bit more about that in a bit. Before I'm going to do that, I will briefly talk about the Pcap file format, which is probably also, you're familiar with it probably. It's the de facto standard used by all the tools we like Wireshark, TCP dump. It's actually developed by the same people, or has been invented by the same people than TCP dump and libpcap. It's pretty straightforward. So what you see up here is the rough structure. Each Pcap file starts with a header that contains some information about the data link type. For example, is this a packet trace that has been sniffed on an Ethernet link or on a PPPoE link or on whatever, some other link. And then you have a list of consecutive packets, okay? These are the individual packets, and the packets also consist of a header that carries information like timestamp, timestamp and some other stuff, the number of bytes captured, and the actual length of wire. So you have some meta information, and then you have the actual data. So this is pretty straightforward, and you can easily create your own Pcap parser or creation utility yourself. It's pretty straightforward. You don't need any library for it. I have printed the header, or some parts of the header file of the libpcap library on the bottom of the slides. It's probably hard to read for you guys, but you see it's really not rocket science in there. Anyways, the libpcap library is an open source library for creating, modifying, parsing those Pcap files. It's GPL, which is good, so you can grab your copy and use it in your own application. It's used by all the famous tools we know. Okay, I mean TCP dump and Wireshark, I already mentioned these. They use libpcap, but Snort as well. It's relying on libpcap and lots of other tools like TCPIC, TCPflow, and actually our sniffer as well, but it doesn't use libpcap for sniffing packets. One important thing to note is that the timestamps that are part of each packet are in microsecond time resolution. So usually your CPU gives you a much finer time resolution, more fine-grained time resolution, right? So you can easily have nanoseconds or something like that. Anyways, these are microseconds. If you want to sniff on a high-performance link, like on gigabit Ethernet or something like that, it's really, really important that you handle the incoming packets as fast as possible. Because if you don't do that, it might happen that you drop some of the packets, which is bad, because you cannot recover these. And also, if you imagine you have a TCP stream and you drop or you lose one of the packets in there, then the whole stream is, well, broken. You cannot reassemble the stream. And imagine this is say an encrypted session here, and you lose one packet, then it's impossible to decrypt the reassembled stream afterwards. Does it make sense? Okay. So the sniffer you design must try not to drop any packets at all. So it must handle the packets as fast as possible again. already mentioned that the performance is depending on memory handling, so allocation, releasing or freeing of memory, and the copying of data. And another thing, the second point down here is actually quite interesting. If you take a look at the standard tools like Daemon Logger, who of you is aware of Daemon Logger, the network sniffing utility? It's actually quite nice because I think it has been written as part of a Honeynet project effort some years ago by by Marky Roche, the inventor of Snort. It's also designed for just sniffing, for just recording traffic. There is no analysis functionality in there, which makes sense. Okay, because usually you want to either record traffic, or you want to analyze traffic. It's two separate, completely different tasks. Okay, so it makes sense to have a pure traffic recorder. But if you take a look at tools like Daemon Logger, they trigger a system call to get the time at every time a packet arrives, which of course is not very performant. Because you can imagine if you request the time from the CPU for each packet, that would mean a context switch, and it leads to bad performance. So you also have to reduce these calls as much as possible. And they're also not even necessary, because if you take a look at the data you get from the network card, the time is already included there. So there is no need at all to request the time for each packet. You can just take it from the information that's already there. Okay, so we designed our own sniffer, our own traffic recorder, Multicap. It's called Multicap because it implements a concept of trackers. You can have multiple trackers in parallel that record different kinds of traffic. You will learn what I'm talking about later on. But we also tried to do what I already presented on. We tried to minimize memory allocations. So we decided to use a raw socket, a PF packet socket, which is a special interface to the network stream. Unfortunately, this is only available on Linux systems. Well, as far as I know. I think it's not available on BSDs and other Unix systems. So this makes our Multicap program not really portable. It can only be used on Linux. That's a little drawback. But on the other hand, if you want to sniff some traffic, for example, in a Honeynet, you can easily set up your own box just for that purpose and put a Linux system on it. So that's one thing. This socket allows us to get each packet directly from the network stream, so to speak. So that's a nice thing, the raw packet, including link layer headers and stuff like that. Then, as I already mentioned, we want to reduce the number of copy operations. So we attach a ring buffer, a special memory space, to this socket and tell the operating system to copy all packets that are received on the network card into this buffer. And this buffer is a ring buffer, so it's circulating. So that means there are no memory allocations taking place. There is no heap management involved, stuff like that. It's a fixed size buffer that just wraps around, okay? And also the other advantage is that we don't have any memory copies from kernel space into user space. So if we want to access this data from within our application, there is no copy operation necessary. And this dramatically reduces the amount of memory handling of system call. Okay, and as I already mentioned, there is no need to trigger a time system call or get local time, whatever, to retrieve the time when the packet was received, because the information is already provided by this PF packet socket structure that wraps the individual packets. And it's also nanosecond resolution, so it's even better than what we have in the Pcap format. Unfortunately, if we want to convert our traces into Pcap format, we lose this kind of information again. But anyways. And third, if we want to write data to disk, to hard drive, then we have to do it in a clever way, in a smart way. So what we do is we use memory map I/O. I don't know if you're familiar with that. The usual thing is to open a file, and then whenever you want to write data to it, you just call write or something. And this is, of course, also not very performant, because you access the hard drive multiple times over and over again. For each packet, you access the hard drive, and this, of course, costs performance. But if you use memory map I/O, you can take a fixed buffer or amount of memory, map it into RAM. So it's actually a part of the file on disk, and you map it into RAM, and then you just write to this memory section. And if you call a flush function, then it's flush to this. So this concept reduces the number of hard drive access. Okay, and these three design goals make our sniffer really, really performant. But we also wanted to have some features in there that make multicap much more usable for us, because I don't know if you are dealing with packets in your day-to-day business, but we do, and we found ourselves in the situation where you have like 3 or 4 consoles open, every console running another instance of TCP dump with another packet filter. For example, one TCP dump is recording DNS traffic, another one is recording HTTP traffic, and the third is recording all traffic because just in case you don't want to miss any packets. And this is of course not really, it's kind of a hack, right? What would be more convenient would be one single daemon that can be configured to record different kinds of traffic and dump it to different files. So what you see on this slide is a configuration example for multicap. So it uses a C-like configuration language, and I will briefly go through it and explain to you what this means. So these are the global options here. They apply to all trackers. So you can specify that you want to rotate dump files, the files that store packets, on a daily basis, but you can also rotate on an hourly or basis or based on size. So every 10 gigabytes, for example. And this is really what you want when you run a sniffer or a tracker in a Honeynet, right? You want to start a new trace file every day, something like that, because you don't want to end up with a 100 gigabytes file that, I don't know, or a file that exceeds the size that your file system can manage, something like that. So this was really important for us. Then you can, of course, specify the path where to store those dump files, and you can define a pattern that is being used to create file names. So this is a variable here that will later filled with a tracker name, and this is a format string. I will show you in the demo how this works. And this here, down here, is a sample tracker configuration. So you have a trackers array. In this example, there's only one tracker. The tracker is called TCP only, and you can imagine what it does. It only records TCP traffic. Okay? There is an enable option, so you can easily enable or disable trackers conveniently just by changing this in the configuration file. You don't have to delete the whole section down here. Then you can specify an interface. And Linux is very cool because on Linux you can also specify the any interface, and then you would record traffic from all interfaces that are configured or up, which is nice. Then you can have a Berkeley packet filter expression that, specifies which packets to record. You know that from TCP dump, Wireshark, these tools. And we actually used the Pcap for this Berkeley packet filter